This program is a presentation of UCTV for educational and non-commercial use only.
Good evening, everyone. Welcome to Science at the Theater's Just Say No to Carbon Emissions, sponsored by the Friends of Berkeley Lab and co-sponsored by the Berkeley Energy and Resources Collaborative. My name is Jeff Miller, and I'm Head of Public Affairs. Our topic tonight is clearly tied to the 40th anniversary of Earth Day, but for all of us at the lab, and I really do mean this sincerely, every day is Earth Day for us. As many of you know, Berkeley Lab is an international center of energy research with a very local flavor. Our scientists, many of whom are Berkeley and East Bay residents, grapple with such huge questions as how to reduce energy demand and increase efficiency, store and distribute energy more effectively, create new sources of renewable energy, improve combustion, and develop innovative materials that will make energy cheaper. So while the title of tonight's Science at the Theater is Just Say No, Berkeley Lab is really all about saying yes, and that's yes to basic science, yes to applied science, yes to policy analysis, yes to finding technological solutions and bringing them to the marketplace, and yes to restoring the planet's carbon balance, which is at the heart of the lab's Carbon Cycle 2.0 initiative. This is admittedly an ambitious, audacious, and some would say outrageously unattainable science agenda. We don't think so, and some of the reasons for our confidence will be showcased tonight. Our first speaker, Ramamoorthy Ramesh, will explain how we are trying to make solar energy more affordable. He will be followed by Nan Zhou, who I think will startle you with her largely untold story about how the lab has partnered with China to reduce that country's carbon emissions. Our final presenter will be Curt Oldenburg, who will discuss how we might be able to safely store CO2 underground. Each speaker will have about 12 to 15 minutes to tell why their work matters to all of you. At the close of the presentations, all three who are seated here in front of me will take their seats on the stage for a question and answer period. So thank you for your attention. Ramesh is going to start us off, so please welcome Ramesh.
First of all, thank you very much for sharing your Monday evening with us. Thank you for supporting Berkeley Labs and University of California, Berkeley. It's a distinct honor to be here with my colleagues to give you our perspective on what this means to all of us. Okay, so my part has to do with the first question, which says, can I make solar energy very cheap? And I want to take you through some of the kind of the prelude to this whole problem by beginning with a very sobering video or a view graph. This is some measurements which has been going on for a while. For those of you who have heard Steve Chu or my other colleague Arun Majumdar, you might have seen this view graph from Steve's collections. Basically, it's measuring the area, approximate area of the polar ice cap as a function of time, and you can see it's shrinking and it's growing depending on the seasonal changes. But what's really interesting is what you will see here. Right around a few years ago, maybe 3, 4, 5 years ago, there's a big drop in the area. And you can go back and say, you know what, this is all just fluctuations in the climatic patterns. Or you can take a more active view of this and say, something is really changing. And therefore, there's a big debate that's going on. And of course, part of the debate is the fact that one has a whole bunch of things that are happening around us. And so we can go back and say, let's take a more proactive look at this. And this brings us to the Tokyo subway map. I make a joke out of it. This looks very complicated, isn't it? So I want to walk you through every one of those stations, all the way from Shibuya to Tokyo Main Station and every other station in between. Okay, but this is a very important view graph. What it talks about is the balance of energy. What do we consume in terms of energy? That's on the left side. And you can see there are three big animals, three big gorillas. Coal, which is about 23%. By the way, all of these are in percentages. That's the total US consumption, which is about 100 quadrillion BTUs. very large number, 10 to the 20th joules of energy being consumed on an annual basis. And you can see we consume about 23% of coal, first bad news, about 23% of natural gas, second problem, and 40% of petroleum, really big issue. And this has two very, very serious connotations to it. One is simply a scientific connotation, which is the amount of carbon dioxide we're putting into the atmosphere. That's the first part. The second part of this has very strong geopolitical connotations, which is something that we need to grapple with as a world, as a country, as a hemisphere. So if I add up all of these, the sources of our energy, 90% of that is coming from what we call fossil fuel. All of these are fossilized into the Earth's crust. Okay, if you look at the top part, that's even more sobering. Only about 10%, and out of which the particular topic I'm going to look at is solar. It's 0.006 on this chart. This is about 5 years old. So it's about 0.1%, approximately of that order. Very, very small fraction of our energy comes from solar. And therefore, there you say, oh my God, this is really a bad problem. But I say, this is a fantastic opportunity to go grab this market share. Okay, so that's one part of the whole story. On the right-hand side of this picture is an even more kind of a troubling picture. Let me take you through that. This is the consumption of energy. How do we use all of this 100 quads of energy? On this side, you have about 20%, 25% of transportation, all the cars, the airplanes, and the trucks that we drive, 25%. Industrial manufacturing, paper, steel, whatever else that we manufacture, takes about 25%, maybe 30% of the energy. The other part is buildings. Buildings consume about 25, 30% of the energy. But that's okay. We need to have all of these. These are all important components. But the big problem with all of this is this red box that I show here. We waste about 55% of this total energy. We throw it away. Every time you drive your car, you're exhausting gases at 600 degrees centigrade. That's basically throwing energy out into the open. Every time a steel billet comes out, it comes out at 800 degrees centigrade. Every time a glass plate comes out of a manufacturing plant, it is coming out at high temperature. You're throwing out that energy. So if you listen to Steve Chu and Arun Majumdar, my other colleague, they will say the lowest hanging fruit is not here. The lowest hanging fruit is making our things more efficient. Let's make them use the existing energy in a better way. So you already get the picture. Energy is not a single animal. This is a multifaceted animal, which really brings us to the center of carbon capture 2. This is our mantra. This is the wagon that we're circling around. It has many components to it. What I'm going to focus on briefly today is solar photovoltaics, how to use the power of the sun to get energy. But a corollary, a very important corollary to that is energy storage. I just can't grab the sun's energy, put it in my pocket. I have to do something with that. So storage of energy, battery technologies are very, very critical to this. Okay, artificial photosynthesis is another way of mimicking nature. Can we use the power that is invested in nature to probe artificial photosynthesis approaches? Biofuels is something that you must have heard of from Jay Kiesling, my colleague, and you will hear today from Curt about carbon capture. Analysis of all of this, how does all of this happen, is a very key component as well. So when you start putting in energy as a picture, one needs multiple components. You also have to worry about the capture of the carbon dioxide that you're putting into the atmosphere. Okay, so let's now focus on the particular topic that I was going to discuss, which is basically capturing the power of the sun. And in reality, every one of us should be a billionaire because so much of energy coming out from the sun. Let me give you some numbers. The sun puts about 120,000 terawatts of power. And for us, we only need about 15 terawatts today worldwide. We need about 3 to 4 terawatts of power for the US of A. So the sun is very capable of making all of us very wealthy intellectually, financially, and energy-wise. The question is, why is that not happening? So let's take everybody through that. These different points on the world are points where there's a huge amount of solar intensity, very large amounts, about 350 watts per meter squared of average solar intensity. So the question that we have to ask is, why did this not happen soon enough? one obvious reason, and a very important reason, is the fact that solar energy is not cheap enough. And I come to this business from the semiconductor side of life, where there's only one important rule, which we all know, which is cost per bit. I will only pay the minimum cost to do one amount of transaction. In the energy business, that's exactly the same argument. It's the cost per kilowatt hour that the customer is willing to pay. So the question that we've been asking from the research point of view is, can I make solar energy dirt cheap? Let me take you through a cartoon. This is home. And what we want to do is to try to take a small slice out of this and ask the question, can I forget about doing any sophisticated manufacturing like we do currently with silicon-based? The stuff that you have on your rooftops is all based out of silicon, which is a very complicated process of creating these materials, putting it on a glass plate. What we would like to do is to instead take a piece of the cake and use it in as virgin a form. So in some sense, we're trying to mimic fossil fuels by using the material in the as mined form from the earth. So if you look at the chart, this is from the Geological Survey, you can see that silicon, of course, is a very popular element. Oxygen, of course, the most popular element. We know why. But silicon, 5,000 tons of it is manufactured in very high quality. Much of that goes to Intel, Applied Materials, Toshiba, Samsung, all of the semiconductor manufacturing people. So this is a very, very high value commodity. On the other hand, if you look in this chart, there are a lot of elements. Now, my favorite element, of course, is iron. It's a very primordial element. It's inside us. It was forming when stars were forming. So we can go back and look at all these mineral type elements and ask the question, can I use it as a photovoltaic material? And so this brings me to one piece of data that I want to show you. And much of us know that Telegraph Avenue is a very interesting place. A lot of things can be obtained on Telegraph Avenue. But there's also a Rosie's bead and a mineral shop. And you go there, you can pick up a piece of malachite. If you could see the malachite in the background, that's a picture of a piece of malachite. I mean, sometimes people use malachite for jewelry or for decoration purposes. Malachite happens to be the primary source of copper. And copper is a very interesting material. Malachite is basically a carbonate of copper. So the experiments that we're doing, and this is really why you need a framework like Berkeley Labs, where physicists and chemists and engineers can all come together to try to solve these very complicated problems. So we use a piece of malachite. And if you look at these curves, these are basically the most important curve that you would like to have in terms of using the material as a solar cell. What we're comparing here is a synthetic material, copper oxide, and looking at its performance, comparing it to a naturally occurring material. There's virtually no difference between these two systems. Have we solved all the problems? Absolutely not. But we are on a track to look at a very interesting alternative approach to silicon or very expensive materials by looking at minerals as a source of photovoltaic energy conversion. The argument here is that now I can start to look at this whole process of photovoltaic energy conversion like I would use coal or any other fossil fuel. Okay. So let me finish up by asking you a question. What is in your mind, what's the most important discovery of the 20th century? Any answers? Car. What else? Transistor. What else? Electricity. What else? Atomic energy. What else? Internet. Yes, I think all of them are fantastic discoveries. But there's a very important discovery, and I'm going to give you the answer in just a second. All of them were great. But could we, as humanity, have lived without all of this? The answer is absolutely yes. There's one thing that we can't have lived. And this happened in the early parts of the century. And this was way back in 1898, just the beginning part of the previous 100 years. This is Sir William Crookes, who was the president of the British Academy of Science, kind of equivalent to our National Academy of Science. He basically launched a kind of a call for all scientists to solve an important problem. Nothing to do with any of the things that we talked about. It had to do with food. Okay? What was happening in Europe is that the population was growing very fast. nitrogen in the soil was depleting, and the bacteria and the biocatalysts were not sufficient to replenish the nitrogen. And so the output of crops in Europe was coming down quite a bit. Okay? That call was heard all through, and of course, we all know what happened. Basically, in the early 1908, Fritz Haber, a German chemist, discovered a process by which catalysis could be used to make ammonia, which is a very, very critical step in forming fertilizer. Okay? And in 1913, an engineer. And this is really the big message that we want to take away. You want people with different competencies, complementary competencies, working together to solve a very big problem. So Karl Bosch, who was the founder of BASF, he developed the mass process to make fertilizers. And we know that this basically solved not only Europe's problems, but in the 60s, the Green Revolution happened. India, China, name it, everybody developed based on the discovery of fertilizers. Now, discovery of fertilizer doesn't automatically mean that one can put fertilizer everywhere and for every reason. So moderation is a very important component. You make a very, very interesting point. But the key point is that there is a first step in all of this, which is triggering the need for food, which all of these discoveries solve. Okay, so that basically brings me to the last view graph that I have. Energy today is as big a problem, or energy in the environment. Energy doesn't go away from environment. As big a problem that you can think of in the past 100, 200 years. Every decade, every millennium has its own set of problems that human beings had to solve. By far, this is a fantastic problem that we all collectively need to work together. We need to have the science and the technology. A place like the Berkeley Labs can really address all of this within the energy framework. We need to exploit the basic science, what we learn from the science, and to create new technologies. Silicon Valley, the Bay Area, is just a fantastic playground. The ecosystem here is just fantastic. We also need to work with the folks who implement policy. Energy is very, very closely intertwined with policy. Of course, we need partnerships. We need partnership between national labs, universities, industry, international. We should not forget that energy is a global problem. India and China are very, very key players. That gives me a very good point to segue into Nan, who is going to talk about the international component of it.
So, Nan, why don't you join us? So I'm curious, for those out there, if those who are renting, would you be willing to pay 10% more to have solar installed and 10% more rent in the solar building? Raise your hands. Those of you. Okay, how about people who own their homes? Would they be willing to pay 10%, 20% more in a tax of some sort to have solar installed? No? Yes? Okay, all great questions. See, priming you for later. And so how about your tax dollars at work for scientists like Ramesh, right? Does that seem like a good idea? Yes, okay, I agree. Okay. Nan, take it away.
Good evening. My name is Nan Zhou. I work for China Energy Group at LBL. And tonight I will be talking about China's energy efficiency policy measures and what we're doing and to help China to improve the energy efficiency. And first of all, a brief introduction of our group. And our group was funded in 1988. And we're probably one of the first group and outside of China and focused on energy efficiency and policy. And probably we're also remain one of the strongest influence in China. Our area of research, mostly we will try to look at what international energy best practice policy is and try to apply those to China. And our area includes appliance energy efficiency. And this is here is a label of the China appliance energy efficiency and then standard. And another area is building codes. And we helped China to develop building codes. And through our collaboration with China and using our simulation model and methodology to help China to and develop those building codes. And also we work with China on the industrial energy efficiency to help their plants to become more efficient, and also introduce the international best practice, and both in terms of the policy and the technology. And we also do modeling, and we look at China's energy consumption current situation, and then we project the future energy consumption, and also looking at the policy impacts and of the different options. And other than that, we also evaluate the effectiveness of this policy to see if this policy were successful and effective in terms of reducing energy consumption and reduce carbon emission as well. And our model of collaborations mostly through bringing international best practice to China. Currently, we have more than 40 projects in China, and we collaborated with about more than 50 institutions in China. And also, we bring in a lot of Chinese counterparts and to the lab and get them trained in terms of methodology, and then to get them to get used to the policies, measures, and technologies developed at our lab. So next slide is about the primary energy consumption in both China and the US. And on the right-hand side is the US energy consumption by sector. On the left-hand side is China. So if you compare these two, and we can see that China's energy consumption is still smaller compared with US. And however, it's been increasing very fast in the last 5 to 7 years. So, but the energy consumption in the US hasn't changed that much in the last few years. And secondly, from this chart, we can tell that that in the right-hand side, the energy consumption in the US, the red and the green is building energy consumption, and blue is transportation energy consumption. And you can see from this chart, in the US, most of energy is used in consumption and driving, people driving and moving goods, and use electricity in their household. And however, if you look at the same figure in the Chinese energy consumption chart, you can see that the red and the green part is very small and only accounts for about 20% of the total, whereas in the US, it accounts for 40%, and transportation accounts for 30% of the total energy. And there's a large gray part in China's energy consumption mix, which is industry. That accounts for about 70% of the total. And if you compare that with the US, that part is only less than 30%. So industry in China's energy consumption is very important. That's why we paid a lot of attention to bringing the industrial energy efficiency measures and technologies to China. And another point we can make is that, Chinese people, they're still using much less energy in per capita compared with the US, and particularly in the building sector. And if China in the future will use as much as energy as the Americans using, so the impact on the world energy consumption, energy security will be very big. That's why we focus on China. And among this energy consumption, most of the source is from coal. It's about 70% of the energy used in China is coal. And so if we look at what that implies, and in terms of the carbon emission, which is the next slide, and we can see that in terms of the similar chart, but this is energy. This is carbon emission, and we can see that China's carbon emission has already surpassed the U.S. to become the world's largest, and also it's been increasing very much in the last few years. Therefore, to address the climate change issue, and China and the U.S. are the key players, and that's why we have to work together to reduce the energy consumption and reduce the carbon emission. Why has China's energy consumption grown so fast in the last few years? And we probably we all understand that in the U.S. and most of the population already live in cities. So about 80% of the people living in the city. And however, in China, this figure is only 50%, less than 50%. And in the future, they will continue to be urbanized. So there will be more people living in the city area. So we, based on the UN projection, and there will be 375 million people and moving into cities by 2025, between now and 2025. This is the equivalent to the entire US population. So we're talking about urbanizing the entire US. So once all these people start living in the city, and they will need buildings, and they will need steel and cement to build the buildings. And that's why in the last few years, the steel production, the cement production, and has increased a lot. So if you look at this chart on the top, and two charts on the top right, and one is steel production, another is cement. And for steel, it quadrupled. The production quadrupled in the last 7 or 10 years, and for cement, it's more than doubled. And basically, China is producing half of the world total production on both cement and iron steel. And once all these people started living in the buildings in city, and they will start by purchasing appliances, and they will use water, and they will consume goods. So if you look at the next chart, which is on the bottom, on the right-hand side, and this is basically ownership of the major appliances in China, and how they grown from 0% to close to 100%, and for most of the appliances. So in the 1980s, a lot of the households didn't have any appliance. And in my family, we had the first TV in the 1981. And we're one of the first family who had a TV because my uncle worked in the TV manufacturer. So he got all the parts and assembled the first TV. So every night we have the whole courtyard, about 18 families, coming to my house and bringing their own little chair and just sitting there watching TV together. And about 20 people, they're all packed. And however, if you look at what happened today in 2006, 7, and most of the households already have clothes washer, refrigerator, air conditioner, TVs, and some of them started having cars. And so with China's continue to get urbanized and getting the energy consumption low and keeping the emissions down will be very challenging for China. We already saw in the early chart that China produced more than half of the world cement, and also steel. And cement uses a lot. Making cement uses a lot of energy, and that's why. And we particularly targeted the cement industry in China. And what we have done to help the cement industry to become more efficient includes policy, bringing the best practice policy to China and developing tools. And for example, we developed this benchmarking tool and for the cement industry in China. In this tool, and a cement plant, can compare their energy consumption level and with the world best practice, and to see where the gap is and where the potential is. And based on the comparison, they can identify the areas where they can improve. And we provide a menu that includes more than 50 energy efficient technology and the measures. And the plant can play around with all these measures and technologies and choose what's applicable for their plant. And they can look at the description of the technology, and they can look at typical energy savings, and also look at the cost, benefit, and the payback period. So the two charts on the bottom shows before and they implement some energy efficient technology, and after they implement some technology. And you can see their energy consumption score in the first chart on the left, and it was 156, which is 146, which is 46% above the world best practice level. But after implementing all these technologies, their score and went down to 114. And so it's only 14% above the world best practice. We don't just and do some research and write a report. And we also do a lot of groundwork in China. And in the past 2 years, we provided a lot of training to our Chinese counterparts and industrial associations and cement plants using this tool. And last year alone, we trained about 300 staff from more than 200 cement plants. And also this year, we're planning to train about 42 cement plants and their employees and to use this tool. And one uniqueness of the work we're doing is that we don't just fly in China and make presentations and leave. And we also conduct all these trainings and work very closely with our counterparts in China. Sometimes we bring them to the lab to work from 6 months to 2 years. And also sometimes we go to China, we stay there for 1 month, 2 months, and just to work with them very closely. And you can see some photos where we're working. And to have some impact, and we really need to understand some of the policy and the cultures and in the local area. For example, and my colleague Lynn Price, who's sitting in the audience, and I went to a lot of cement plants to provide the training. But in some of the provinces, they have very heavy drinking culture. So they will force us to do bottoms up, and they have different cultures in different areas. So I don't mean that we have to, we just play like a drink all the time, but that's some type of culture we need to understand. And another example in helping China to improve the energy efficiency is in building areas. I just talked a little about the appliance ownership has increased from 0% to 100%. China only spent 30 years to achieve such growth from 0% to 100%, and which took US 100 years to achieve the same ownership. So if we can go to China and have early intervention in the form of the standard, minimum standard and the labeling program, that would deliver very significant savings. And in the US, as we all know, that we have developed a very strong program called Energy Star, and I think you all see them on your computers, refrigerator, air conditioners. And so we introduced this Energy Star program to our Chinese counterparts, and we brought them to the lab and trained them to and use some analytical tools we use to set up the standards. So they stayed in the lab 6 months or a year to learn the methodology, not just the solution. And so in the end, they can pretty much build their capacity and conduct independent research and develop a standard all by themselves. So now today, and they have about standards for 30 products, and then voluntary labeling program for 40 products, and mandatory labeling about 19 products today. And there's a symbol on the left hand side, which is the information label. And you can see that there's different class. It's called class 1, class 2. Class 1 is most efficient, and class 5 is least efficient. And above class 2, which is class 1 and 2, is equivalent to the Energy Star energy efficiency level. So again, we do a lot of underground work, and we provide a lot of training to our counterparts. After we introduced all these policies and measures developed or implemented in the US and the developed world, and we also need to evaluate the effectiveness and whether they've been successful, whether they have saved any energy. So in terms of this appliance standard and labeling program, and we did impact analysis to look at how much energy is being saved. So we can see from the chart that by 2020, and the electricity consumption and can be saved by 11%, and just by implementing these appliance standard labeling program. And this figure in the US is 13%. So the energy star has been started in the 70s, and it took the US 30 years to achieve the 30% of the electricity reduction. However, in China, even though they started late, and they're catching up with what's being achieved in the US. And that's what will be saved is equivalent to about 28 gigawatts can be avoided in terms of power plant investment. And however, again, given the increase of the urban population, there will still be millions of appliances being purchased. Therefore, and introducing and continue to develop and revising the standard and labeling program will be very important for China to achieve the energy efficiency. So last slide, I would like to show you some of the results from all these policies put in place by the Chinese government. And this line basically shows energy use per dollar of GDP produced. And you can see that from 1980 to about 2002. And China has achieved a decline and decrease of the energy intensity, energy use for producing $1. And that's because during those 20 years, China had a very strong energy efficiency program, had ministries who's in charge of energy efficiency and energy quota and various measures, and to keep the energy consumption low. And basically, they achieved their target by quadrupling GDP with only doubling energy. However, the situation has changed since 2002. And you can see from the same chart, this intensity has gone up, and by 5% a year, and in those 4 or 5 years. And that's because of the opening markets and joining WTO, with China becoming the world factory. And also a lot of the energy efficiency program got abandoned, and the ministry was dismantled. So as a result, the energy intensity has gone up, and the Chinese government realized this is not sustainable. So they have to do something. And in 2006, they announced this massive target to reduce the energy intensity by 20% by 2010. So that's basically reducing 20% in 5 years. And we already saw that in the early years, China achieved the decrease of the energy intensity. But at the time, and in the beginning, they started at a very low level. There wasn't any appliance standard. There wasn't a building code. So it was relatively easy for them to achieve such goal. However, after 2006, and a lot of the low-hanging fruit has already been captured. So it became much more challenging for China to reduce the energy intensity. And however, and with a list of policies Chinese government put and implemented, and they have been able to put this put this energy intensity back on track. As you can see from the chart, it decreased annually around 4% and until 2009. And what we just learned a month ago, that they are not doing very well last year because of world financial crisis. And so we can tell they're struggling a lot to meet the target. And so, there's a list of the policies and Chinese governments implemented to achieve targets. And if you're interested, we can elaborate a little bit later. That includes the efficiency policies for buildings, appliances, and also for industry, and as well as power plant renewables, and also the investment. So even though this is very challenging for China and to achieve all these targets and then keep the carbon emission low, And but if we hope to bring this carbon emissions down and get it under control, China has to do it. With that, I will close my presentation. Thank you.
So I think this is a great untold story, but so I'm curious, has anyone heard of the China Energy Project other than those who are here who actually work in it? Raise your hands. Have you heard of it before? Just a few. Okay. I recommend the latest issue of Wired magazine. It's a story with Steve Chu, our former director, talking about the importance of partnership with China in reducing greenhouse gas emissions. It's a great story. Next up is Curt.
All right, so I'm going to talk about another way to say no to carbon emissions, and that is the approach of geologic carbon sequestration. I'll describe what it is, how it works, why we need it, and some of the potential impacts that it may have. So the motivation for this approach is shown here in this sort of stripped down schematic of the global carbon cycle. What we see here are fossil fuel combustion producing carbon emissions in the form of carbon dioxide. And this is occurring at a rate that's much faster than either terrestrial ecosystems or the oceans can take up. So we have photosynthesis going on, we have uptake in the soils, but it cannot keep up with the rate that we're putting it into the atmosphere. Similarly, in the ocean, it's taking it up, the pH is going down, but not at a rate great enough to keep concentrations in the atmosphere stable. So these are going up, CO2 concentration going up. This is causing greenhouse effect, which leads to global warming and the associated climate change. So the idea for geologic carbon sequestration is to just cut off these emissions right here from point sources, take that carbon dioxide and inject it deep underground where it will stay indefinitely. Looking at this in a little more detail, we see here a point source of CO2, such as a coal-fired power plant. I'll just show here the whole chain of processes involved in this. We need to capture the CO2 from the flue gases coming off of this power plant. So this is a step that needs to be done. Once we've captured the CO2, we'll need to compress it to put it in a liquid-like form that makes it efficient to transport. That transport would be done by pipeline where necessary. We would transport it, sometimes great distances, to places that are very nice and well capable of taking the CO2 through injection and storing it deep underground. So I'll focus now on this step here. So what's shown here is a real schematic cross-section of a sedimentary system somewhere in the Earth's crust. We have an offshore section and an onshore section. These areas exist throughout the world, not everywhere, but in many places. What's important to remember for the crust of the Earth is that there are not large caverns or large void space. The fluids, the water, the oil, the gas, the things we know about that are in the crust of the Earth are actually in the pore space. So most of it is grains cemented together with pore space. So what's shown here, for example, a familiar sort of an offshore platform, and we know there may be oil or gas trapped in sedimentary formations, and that stuff can be produced. Those are fluids that are basically, they've been sequestered there for geologic time. So the idea for geologic carbon sequestration is to kind of do the reverse of our extraction of hydrocarbons. We want to put that CO2 back. So illustrated here are several different scenarios. Let's just look at this number one here first. This is an injection of CO2. You see this nice structure here to take it. The darker brown rock here would be a low permeability rock like a shale. And the rock that it's being injected into would be a higher permeability, higher porosity rock like a sandstone. So the CO2 comes in, is injected, and then it stays there because it cannot rise through that lower permeability rock. Note that the depths here are quite large. This is more than 1 kilometer. This is because, again, we want to store CO2 at depths where it's actually in a liquid-like form and it's actually quite dense. So how big a role can carbon capture and storage play? What we're seeing here are our emissions from fossil fuel use of carbon dioxide globally. We emit globally, about 30 gigatons of CO2. So we're somewhere here in 2010. It's possible this has gone down just a bit with the global recession, but we're somewhere in the range of 26 to 30 billion tons of CO2. If we keep on a path as we've been doing in terms of growth of population, manufacturing, et cetera, we would increase our emissions along a curve like you're seeing here. And it would put us out in 100 years or so at about 80 billion tons of CO2 per year. So concentrations in the atmosphere would rise a lot. What we want to do, what LBL and other people concerned about this are trying to do, is to take away those expected emissions. So that's represented by this shape here that I'm describing. If we can find a way to not emit along this curve, but instead to emit along this curve, we can reduce our emissions relative to the business as usual and maybe keep global warming to something along the lines of 2 degrees C or so. If we keep going like this, we'd be up 4 degrees C or maybe more. These are very uncertain numbers. So how do we do this? People recognize that there's no one answer to this problem. It's a huge, huge problem, but they can envision piecing together various solutions. So here you're seeing conservation and energy efficiency. That's something that we can do to account or displace this much of the expected emissions. Similarly with renewables like solar energy and wind, if we can grow that as a fraction of the energy that we use, we will not have equivalent carbon emissions. And onward, if we can switch and start using more natural gas, which is a lot cleaner than coal, we can increase that contribution and not emit that carbon. And finally, you'll see this huge role here projected for CCS. So some people think CCS can be really one of the most important components of avoiding this emissions wedge. So this is shown here, just rough numbers of ramping up from something like a gigaton per year, which maybe we could be doing in 15 or 20 years, ramping that all the way up to 15 gigatons per year, say in 90 years or so. These are big numbers. What do these things look like? All right, so here's the city of Berkeley. This is a cubic kilometer box here that I've just sketched onto that. If this box, just as it was filled with water, this would weigh 1 gigaton. So remember, Earth's CO2 emissions are about 30 gigatons of CO2 per year. If we took carbon dioxide at those liquid-like conditions that I'm telling you exist deep in the Earth, it would be maybe 30% larger of volume than this. So a gigaton of CO2, just in its liquid-like reservoir form, might be 30 to 40% larger than this. Now, bear in mind what I said about porosity. This fluid is occupying only the pores of the rock. So in fact, it would occupy considerably larger volume. But this gives you some idea for the magnitude of these emissions. So what makes us think that the CO2 is going to stay there? Well, shown here is the figure I'll point you to, which is a very classic figure showing the trapping of natural gas or methane and oil and water. So oil and gas and water here have stratified themselves based on their density. These are light fluids. They float up over geologic time, again, through the pores of the rock and accumulated up against this shale cap rock, this low permeability rock. So this is a storage phenomenon that Mother Nature played out. These fluids are there in a reservoir form. We drill wells into them and produce them. This is exactly what can be mimicked for carbon dioxide. So the first order trapping mechanism is the simple one that you see here. It's called structural trapping, and it's analogous to the way oil and gas are trapped naturally in the Earth. Now there's another very fundamental trapping mechanism, and that's the second one. It arises when CO2 and water are moving through the rock. For example, the CO2 rising buoyantly and water coming in behind it. Small blobs, little bubbles of the carbon dioxide, even in this liquid form, get trapped as this flow process occurs. And it's sort of like when you have a sponge and it's filled with water and you let it drain. That sponge isn't dry. You really have to squeeze it to get the last bit of water, and even then it's not dry. So this is the residual CO2 that stays behind during the flow process. What this means is that you don't even need to have a closed structure to trap CO2. If some small amount of CO2 were injected here and simply allowed to migrate through the pores here, it would actually all become trapped after migrating some distance. So this is the second trapping mechanism. A third one, very fundamental, is simply dissolution. The CO2 will dissolve into the brine at depth, just like a carbonated drink. And in fact, when that happens, the water, the brine, becomes even denser than it was before, so it occupies less volume and tends to stay down. So we've got structural trapping, we've got residual gas trapping, and we have solubility trapping. The final one is really the holy grail, the most stable form of trapping, is if this CO2 would react with minerals, react with components in the brine, and create a carbonate mineral. So we know this does occur, but it occurs very slowly. So there's research going on at LBL to speed up this sort of reaction to make carbonate minerals, make a very stable form of geologic carbon sequestration. So where can CCS be carried out? Well, I haven't shown you the sources here, but you can imagine there's a lot of coal-fired power plants throughout the eastern part of the U.S. and some in Arizona and New Mexico. Out here in California, it's mostly natural gas. So those are the sources. The sinks, though, I've shown here in blue. These are sedimentary basins in the United States. These are typically where we have oil and gas, which is shown in the red, by the way. So oil and gas producing regions tend to overlap with these sedimentary basins that are very nice places that CO2 can be injected. So this is a U.S. snapshot of where carbon sequestration could occur. Note that it's not anywhere. It's not in volcanic regions. It's not in the Sierra. It's not in granite, et cetera. So they're very specific places. Now, there's plenty of geologic carbon sequestration going on now. There's an offshore project in Norway called the Sleipner Project, which has been injecting about 1 million tons of CO2 per year since 1996. There's a very similar project in Algeria that's injecting just about the same amount since 2004. The source of their CO2 is natural gas. So it's a natural gas source that's too high in CO2 to sell to the public, so they strip the CO2 and re-inject it into rocks nearby the reservoir. Okay, so we've talked about what it is and how it works. I'd like to talk now about some of the impacts. What's going to be the effect of doing this? So sketched here is just a schematic of the depth and then something about the health, safety, or environmental impact, just all very qualitative. So recall, we're going to be injecting CO2 if we do this at great depth. And these are some of the impacts, some of the things that could occur. I'll start actually at the top here. So on this scale, these would be the most serious health, safety, and environmental impacts. So just about the worst thing that could happen is if somehow there were a horrible leak and CO2 came up from where you injected it and got right up into the ground, above the ground. CO2 is a dense gas and it flowed over the ground surface. This would be a very, very serious health and safety issue. Similarly, if it were to seep into your house or into your basement, again through a pathway that no one knew about, accumulating at a topographic low, all of these could have impacts on animals and humans right at the ground surface. Now, we typically cannot find any route, any path for these events to occur. So moving down, we have things that are happening in the shallow soil. It could affect the roots of plants and trees. Again, if there was some sort of pathway that we didn't know about. The vadose zone is the area right above the water table. This could also be impacted. Probably the most serious regions or potential impacts that are of concern are CO2 leakage from depth up into potable groundwater aquifers. So this would be a water resource potentially contaminated by CO2. It's not so much the CO2 itself. We know we can drink Perrier and Calistoga, but it's what that semi-acidic water would do to surrounding minerals in terms of bringing components in. It might degrade the water quality. The second most interesting impact of concern recently is this question of induced seismicity. So when you inject fluids in the ground, you do create what's called microseismicity, earthquakes that cannot be felt in the region of the injection zone. And this has caused a lot of concern, and we're doing a lot of research on it right now, whether some of those earthquakes could be actually big enough to be felt and could lead to any damage. So these are really the two main impacts that are of concern today. Again, there's no pathway that people can see that's reasonable to allow these more serious ones to occur. So given those impacts, why are we considering doing this? Why might this be a say no to carbon emissions strategy? Well, what's plotted here from the IPCC is, again, impact here on this axis in several different categories. And right now, the global atmospheric temperature has risen by about 0.8 degrees C. So we're somewhere right in here due to our excess CO2 emissions. And we can see now the impacts on food, the potential for rising yields in high latitude regions. They're seeing this, longer growing season in some places. But if we keep going, again, on that curve toward 2 or 4 degrees, there could be drastically falling yields in many areas, particularly developing countries. With respect to water, it says here small mountain glaciers disappear. Water supply is threatened in several areas. We're seeing this in South America and Peru, where they rely on glacial water sources. But again, if we go further up this chain, you could have just significant problems with droughts, et cetera. And onward to ecosystems, this says extensive damage to coral reefs. We're seeing the bleaching, the pH of the ocean is definitely changing and affecting the ecosystems. So all of this figure is to say that there's strong motivation to do something about our fossil fuel CO2 emissions. And geologic carbon sequestration is one approach that we're doing research on to test its effectiveness and feasibility. Thanks very much.